Alright, so this is number 2 from the optimization activity that we began in class. Alright, so we're to find two positive numbers such that the sum of the first and twice the second is 100 and the product is a maximum. Alright, so the thing you got to remember with these is that you generally are always going to have two equations. One of them is going to be a constraint and one of them is going to be the function that you're going to maximize. So in this case, the constraint is this part. The sum of the first and twice the second is 100, right? And the fact that we're looking for two positive numbers. So what we're really given here is that we have two positive numbers, x and y. So x and y are both greater than 0. And we also know that the sum of the first, which is x, and twice the second, which is 2y, is going to equal 100. Alright? And what we're trying to find, of course, is the product. And we want to maximize that product, right? So what we're doing here is we're finding a maximum of the product of the two numbers. Okay? So remember what we had to do here is we had to somehow take the constraint, which is this, and solve it for one of the variables, because again, the problem with this equation here, m equals x times y, is it's got two inputs. So we need to somehow solve this one for one of the variables. So of course, if you have x plus 2y equals 100, the easiest thing to solve for is x, right? Because it has no coefficient. The coefficient is just 1. So if we just subtract 2y from both sides, we will have x equals 100 minus 2y. Alright? So now what ends up happening is we can take this 100 minus 2y and replace x in this product function for it, right? So what we can do is now the equation that we're going to maximize is x, which is now 100 minus 2y times y. So now we only have one variable, okay? And of course what we can do with this is we can distribute, so we would have 100y minus 2y squared. And now remember, since this thing is really a parabola, right? It's a quadratic function. We can find the maximum, right? Because this thing looks like this, right? Because a is negative, so it opens down. So we have a maximum point here. And where does this maximum occur? This maximum is going to occur when y equals negative b over 2a. So b is 100, so negative b is negative 100, and a is negative 2. So we have 100 over negative 100 over negative 4, which is just 25. So if we know that y equals 25, and we know that x equals 100 minus 2 times y, which is 25, we know that x equals 100 minus 50, which is 50. So there's basically our solution. The two numbers that we have are y, which is 25, and x, which is 50. Alright? So the answer is, you see, write a complete answer. Here's my complete answer. The two numbers are 25 and 50. So there's your answer. All right. Now you notice the optimized step was really what I did when I did the negative b over 2a, right? And the domain, it wasn't really necessary in this problem. The domain you basically get from this, the fact that x plus 2y equals 100. So really what has to happen is, since there are two numbers that are both positive and they add up to 100, the domain is that x and y had to be less than or equal. Now number 3 on this optimization activity is very similar to number 2. It's just more of a word problem. All right. So again, we need a constraint and we need a function to be optimized. Right. So in this case, the constraint is that there's a gardener that has 140 feet of fencing to fence in a rectangular vegetable garden. And we're trying to find the dimensions of the largest rectangular area she can fence. All right. So the given is the fact that we have 140 feet of fencing to fence in a rectangular vegetable garden. So a rectangle looks like this, kind of, with more straight lines, right? And we have a length and a width. So if you're fencing around the outside of this, we're dealing with the perimeter. So the perimeter of this rectangle is 2L plus 2W. And we're assuming that we're using all of this fencing. So when we add up these 4 sides of the garden, we should end up with 140 feet of fencing. So 2L plus 2W equals 140. And we're trying to maximize the area, which is length times width. Okay? And just as with the other one, the idea now is to take this constraint, right? Because the problem with the find m equals LW is that it's got 2 inputs, right? L and W. So we have to solve it for one of the variables. So either one is just as easy to solve for here. So let's say we solve for W. So you subtract 2L. So you'd have 2W equals 140 minus 2L, and then divide by 2. So we'd have 140 over 2 minus 2L over 2. So we end up with W equals 70 minus L. Right? So now the equation to be optimized is no longer just m equals LW, it's m equals L, but now we're going to replace W with 70 minus L. So this is going to be L times 70 minus L. And just as with our last problem, this, when we distribute, is going to be a parabola that looks like this. It opens up. And where is that maximum going to occur? That maximum is going to occur when L equals negative 70, right, negative B, over 2 times negative 1, right? That's A is negative 1. So we get negative 70 over negative 2, which is 35. So the L is 35, and the W is going to be 70 minus 35, right? We got that right from up here. 70 minus L becomes 70 minus 35, which is 35. And in this case, our domain really was that L could have been anything technically between 0 and 70, right? Because could you make a really long but not wide at all rectangle? Something that would look like this. Sure you could, right? And you could basically make this like 69, 69, but then that would only leave 1 and 1 for the widths, right? But are you going to want to make it like that? Of course not. So the best way to do it is if we make the length and the width both 35. So the area is maximized when L equals 35 feet and W equals 35 feet. So what do we really end up with in this case? We actually end up with a square. And in general, that's the case. If you want to form a rectangle with a given amount of material that has a maximum area, what you're going to do is you're going to turn it into a square, right? Because that's going to be the biggest possible area. All right, so you make it 35 feet by 35 feet.